Okay, and the last talk for this session, I think, by Théo on dependent ghosts.
Right. So indeed, I'm adding to the pile, as Jocelyn was saying. But I'm also, this was on the way to also pursue the goal of trying to have extensible type theories. But indeed, so today I want to talk about ghost types and equality reflection. So I will start with the example of vectors, like the usual example, right? So you just have a type-based invariant for lists that just looks at this, keeps the information about the size. And then if you want to write the reversal of vector, which is also the example I use all the time, so you can, if you want to write it with an accumulator, like you would do for list, to have a tail recursive definition, then this is how you would write it. But then Coq or whatever would complain that there is a type mismatch because you have the sk plus m versus k plus sm, and we would like really to say that those are the same things, but they're not. So in practice, you need to have some transport to rewrite along this equality. But for now, I won't write them, and I would just add some asterisk there to say that we can forget about this for now. Then if you extract this to, say, OCaml, you also end up with problems, namely that in the cons constructor, you still keep a natural number. And this is not an information that you would like to have around. And this is even worse if you extract the reversal of vectors, because as you can see, the natural numbers arguments are still there, even though you don't really use them. Actually, this is funny because the pretty printer actually puts an underscore for one of the arguments, so it knows that it's not really necessary. One of them, though, is kept, but for no reason. And you can compute, and then you have some, you perform useless computations. Okay, so I want to solve those problems. And like the idea is that I would like to have list here, like not this natural number should be gone, and those two should be gone as well. So yeah, the problem is always the index of the vectors, right? Maybe we should just use list. That's what people do in the end. But I'm trying to offer a different solution. So this is again in the spirit of the erasure modality that you have already in other languages. This is not new, but maybe a different presentation of it. So in the index of the vectors, I'm marking the natural number as erased, and that means that at extraction, I want it to be gone. And the erased, here I see it as a special kind of type in the universe, which hides a value into erased. So this lives in the ghost universe. And then I have some restrictions, so similar to what Jocelyn was saying. Essentially, I cannot, so I have an eliminator that I call reveal, and I cannot go into type. I can only inhabit ghost or propositions. And here, indeed, so here I have to use hide 0, and for the successor, I need to use the reveal operation, but that allows me to open up my erased natural number to produce another erased natural number, and that's allowed. On the other hand, if I wanted to write a function from erased bool to bool, then it would have to be the constant function. I can't use it. I can't like open a box and see what the boolean I've hidden to produce an actual boolean. And then I want to have a limited form of reflection, which makes things maybe work, is to say that whenever two ghost values are equal, then roughly speaking, they're convertible or definitionally equal. which means that suddenly this definition of reversal vectors type checks. If you have some automation or some, because suddenly it becomes undecidable, but let's say, something like F star would figure it out. So in practice, it works. Right now, this is a valid conversion. And well, there's a prime here because this is not exactly plus, it's a plus where you have to use reveal, but basically it works, okay? But then if you look at this, you might be wondering, well, maybe that's just propositions, right? This is the squash instead of erased. And then, sure, reflection is a special case of proof irrelevance. I can just say that any things that are ghost, I can just equate them, and then I'm done, right? But I still want to have some my index to be informative. I want to say that if I have a vector that's of length 0, then it has to be nil, and so it's not the same thing as a vector of length successor. So I have to be able to distinguish between two different notions, two different erased values. But if you know how you usually distinguish values, then you will know that this restriction of eliminators is a problem. So let's see how it goes. So, well, this is just a notation. So the reveal says that if I have some erased value and a predicate over erased values that I can prove for every actual value, then I can prove it for this one. And here there is a restriction that the predicate has to land in the proper ghost. Right, and then there's the computation rule, the usual one. So the discriminator that I want is essentially I want to be able to inhabit the D of a height 0, but not of the successor or of 1. And to build it, I would try essentially to reveal and say, well, now I have a natural number and I know how to distinguish natural numbers. 0 is true and whatever else is bottom. But here, there is this issue here that the predicate, which I've hidden, is essentially I'm building a proposition, which means that I'm actually going to type. So that doesn't work. So the solution that I propose is maybe a bit weird, but I have a model for it, is that I also allow myself to build propositions. So it's essentially the same eliminator, but instead of saying that it has a return type, it's a proposition. And then the computation rule is no longer a computation rule, because my model doesn't validate it. So it's just a logical equivalence. And then suddenly you can just do the same construction and it works, well, except that you have logical equivalence, but that's still enough to distinguish things. Okay, so how do I justify this property? Okay, like the reflection for ghost types. Well, I'm interpreting it to a type theory which has just ghost types, but no ghost reflection. So instead of the reflection rule, I have a notion of cast operator. So essentially, it's an eliminator for equality, but like especially for ghosts. Okay, and then I can do a translation of every derivation where I replace every use of the conversion rule by a cast, which is something that I've done and other people have done. Like Nicolas Houry, to go from extensional type theory to intentional type theory, except now it's much easier. The proof is really, like it's just one file in Coq, and it works because I have this extra property that casts are ignored for conversion. So when I have two things that are convertible here, they're essentially still convertible in the target, so I don't have to deal with higher coherencies, which like in this case, was done by having UIP. So here, I don't need to have like UIP for everyone, just for ghosts. But sure, that's nice, but my model still has ghosts, so how do I justify this one? And then now I go to more a safer territory, which is just Martin-Löf type theory or calculus of constructions with like strict propositions. And this one is a parametricity translation, which also takes inspiration from exceptional type theory, which was introduced before, so that's perfect. And for the rest of the talk, I'm going to focus on this part, on this model for this ghost type theory. Okay, so the idea is that the first thing you want is to be able to get rid of ghosts, because that's how you get rid of ghosts, right? So I have to construct, I construct the translation that goes into like CCU MLTT, like this, and the property is that if you're in a relevant universe, then you have a translation, but if you're in ghost or prop, then you're gone. Your erasure is undefined. So this fact means that I can't use like prop or ghost inside the new translation. And then we in fact have mode, so it's the same story, but I don't use A in a certain type, but instead that T is of mode T, ghost or prop. And then the translation says that if I have a relevant variable, then it stays the same. The others are undefined. If I have a cast, I just get rid of it. It's not needed. If I have a lambda, then it's just I just recurse, unless the argument is ghost or prop, in which case I just get rid of it. For application, it's as you would expect, well, except when the argument is ghost, in which case you don't need it. But then the question is, how do I do with like the X file, so the eliminator for the empty type? Because here P is a proof, so it's gone. I don't have access to it, but I still need to produce some A for any A. So the solution is intuitively to have an exception here. I don't know what to do, so I'm just going to say, well, whatever, this doesn't happen. So it's a bit like an assert false in OCaml. I mean, if you think of erasure as extraction somehow, you're just saying this is an inaccessible branch, so I can put garbage in there, it doesn't matter. And for this, I use the exceptional translation from Théo Winterhalter. And the type is no longer just translated to a type, but also to a point in this type. So suddenly everyone becomes inhabited. And then I just use that special point, which is the exception, to inhabit my X file. And then, well, I have the universe needs to be itself a pointed type, so n contains pointed types, which is encoded this way. And then you have several projections. So EL gives you the carrier, in which case, like if for the error, we just return whatever. And the error gives you the point. And then this is how you define the translation for types. It's just EL of the translation. And the error is propagated this way. But okay, now we just have an inconsistent model, so that's not a model that we really care about. So we add parametricity on top of it. So this is again just taken from the work of Théo Winterhalter. And the idea is that you produce for every type a proposition that guarantees that no exceptions are raised at top level. And at least when you're in mode, in the relevant mode. I need to use parametricity in prop, or at least I think I need it. I hope I don't need it, because then I can do better. Because if I use parametricity in prop, then it limits my elimination, so I have no large elimination. And I was too sad to have that on the slide, so like this week I at least showed that you have it for bool and you have it for all small inductive types in the sense of Christine Paulin. But okay, that's just a small note. For propositions, you just preserve them, essentially. So that means that the empty proposition is preserved, so you get consistency, and then now this is an actual model. And for ghosts, well, it's special because you still have the same thing. You have a proposition that guarantees that there's no exception, but your ghost value has been erased, so we need to revive it to talk about it. So this is something that's new, or it's inspired by resurrection from Frank Fenning. So you just try to get back what you erased. And so if you have hidden something, well, you just take the erasure of that thing. If you revealed something, you can do the computation to get back the thing. Oh, sorry. And then application just cases on the mode of the argument to know what to do. So maybe it would be clearer with an example. So if you take the booleans, well, true and false, then the erasure is just some new pointed type which has a special exception. And the parametricity predicate says that actually the only ones that are valid are true and false and not the exception. And then using this model, we can show that we have a free theorem. It's just one special case. I guess we can get more. That the erase bool to bool is necessarily a constant function. I do it using, I didn't want to also prove like the identity type for type, so I just used the impredicative encoding. So I say that if I have such a function, then f applied to true is the same as applied to false. And in the model, this becomes this proposition, which, if you could see it down there, it's essentially the identity, so it's proven trivially, thanks to proof irrelevance. And the key is that the function was erased to just a Boolean. So yeah, I mean, the model says it has to make a choice already. And then comes the vectors, that's what we started with. So same definitions before. Then you can define the erasure of vectors, which is now essentially lists, except that you have the exception. And then the predicate is maybe a bit involved, but essentially it says that if you give it a natural number that has to be not an exception, then the vector is of length n. So here you say that the vector v nil is indeed of length 0, and v cons is of length successor of n, provided that v was of length n. Okay, and then now we see actually why we need to have some revival. It's because the n needs to be reconstructed somehow. And well, in this model, well, you can also validate, of course, the computation rules for the eliminator. Well, except that I have some weird rule for the cons case. So here you would expect to see that I reuse here the n that's coming from my constructor, but computationally that doesn't work because essentially it's gone, it's ghost, so I can't reuse it even on the right-hand side. So I don't know, that's a weird rule. I didn't see anything like it, but that's what my model says. So, okay, so just to conclude, we have this translation from like ghost reflection to just ghosts, and then to more traditional type theory. This allows us to establish conservativity and consistency results, also some free theorems. We can also distinguish like type formers, so we still get some nice properties. I think there's still a lot that could be done. Like, how do we deal with inductives? That's a question. What about reduction? Or so do we have subject reduction or termination? It's not so clear since you have those casts that make sure that you need that you are well typed, but you can ignore them. So that's a thing that Ewan here is going to look at. I think there's also interesting stuff to be known about decidability, and one of the motivations is also that it could apply to the meta theory of F-star, which has these ghost types, but I think it has more stuff, and I believe that this is is better behaved. So all of this was formalized in Coq. This was painful in some way because erasure gets rid of certain variables in the context, while parametricity adds some of them, but it's not like you don't have the usual arithmetic that you can just do ×2, or because you have to look inside the context, and I didn't want to have to do that, so I'm doing some weird stuff where context can have holes in them that some variables point to nothing. I use autosubs too, so yeah, substitution was part of the theme these 2 days, but yeah, I use the tool to do it for me. It does everything that's needed, at least syntactically, but I still have to prove the substitution theorem, and I think automation can clearly be improved because it's in the end it's taking so long to just check vectors. So that's it.
One, two, yeah, no, it works. Thanks for the talk. It was really nice. I was wondering, you showed us these vectors and dependent products and sorts, but do you have equality types, like in identity?
So I have the equality type for ghosts.
Yeah.
And I didn't like formalize the usual identity type for the others. Like for the examples, I just used in predicative encoding.
Okay, so you never have to consider the case of an identity type applied to an erase type? Like, because I was wondering, basically in the rule that you had for the vectors, for the when you were recomputing the ghost length of the thing, I was wondering whether you could, like, what would happen with an actual identity type where you couldn't recompute? Like,
So I think the length is essentially, I think it's maybe connected to ornaments, but I don't know enough about them to know. But it's in some cases at least you can recompute. But for equality, I think it's also related to what Ruslan was saying. I'm not sure we want to have a special ghost equality that lives in ghost. I mean, if that's what you're asking.
No, I was thinking more of identity type in type.
So the equality type in type doesn't let me compare things, erase things, because they live in ghost, and for that I have the ghost identity type, and this one I know how to handle. So that's why I didn't. I think they're orthogonal. So basically, you have an identity type for each universe, or you have a different way to do it. Yeah.
Okay. Thanks.
Any other questions?
So maybe kind of related to the question of decidability, I guess if you want to have something where you have some guarantees about this, you'd want somehow to carve out a fragment which has some sort of decidable equality, or at least a fragment on which you can throw SMT solvers or something and hope they will give you some reasonable answer. And so I was wondering whether you thought about like what would be needed to add something like this, so that you can say my index lives in a reasonable place, and so the reflection of equality there I can send to an SMT solver or something.
Okay, so if you go to the top with the reflection, so I mean, one of the motivations of ghosts is also that actually it doesn't matter how you found. If you find a solution, then you know it doesn't matter by design. So that's one of the reasons why I think it's better, like for F-star, that it doesn't matter. So I can just go ask an SMT to give me a proof. I think what's decidable, but this is just conjecture, of course, is which ghost equalities you need to know, you need to prove in order to have your type. So I think you probably have, you can find exactly the constraints that you need. Because, and this is also important to have type format discrimination. So it says that essentially it doesn't pollute the thing because you have, just because you have ghost reflection doesn't mean that suddenly an arrow type is going to be the same as bool. That's not happening.
So I guess my question was whether you can somehow put like type, like, I don't know, constrain your type system in such a way that you know that all the equations that you will generate, that you're going to offload to somebody else, at least live in some maybe reasonable types, so that there's a chance that an SMT solver will find a solution. Because like, if you throw an equation between natural numbers, then there's a chance. If you throw an equation between higher functions at crazy pi types or something, then probably the SMT will not be able to even.
Right. So to be honest, I'm not even sure exactly. I mean, if you have indices that are higher order, it's not clear what happens even with the model. Because if you look at erasure, it's getting rid of dependency. So, I mean, if you have dependency on ghosts, then you might end up with something weird. And I didn't look at examples because I don't know simple enough examples that where this comes naturally. So this would be interesting, but I don't know.
Thank you.
Okay. Are there more questions? If not, then thanks again, Théo.